What if the answers to the biggest questions about existence, where we came from, what the universe is made of, and how it all ends, aren't hidden at the edge of space, but deep within the laws of physics themselves? From the tiniest quantum fluctuations that may have sparked the Big Bang, to the largest cosmic voids stretching across billions of light years, this is the story of everything. In this documentary, we'll journey through the origins of the universe, decode the mysterious structure of cosmic space, explore chilling predictions about its ultimate fate, and ask the boldest question of all: did time exist before the beginning? And can it be bent, reversed, or even transcended through quantum physics? Brace yourself for a mind-expanding expedition into the known and unknown, guided by cutting-edge science, ancient starlight, and the relentless curiosity that defines us as a species. Let's begin with a question. What is the edge of the universe? And more importantly, can we ever see it? Welcome to the fascinating world of cosmic horizons. As vast as the universe is, what we can see is not infinite. It's bounded by light, time, and the relentless expansion of space. In this chapter, we'll unpack three fundamental concepts that define the observable universe: the particle horizon, the event horizon, the Hubble sphere. These aren't just abstract ideas. They shape what telescopes can detect, where galaxies appear, and ultimately, how we understand the universe. Let's start with the most intuitive boundary, the particle horizon. Think of it as the furthest distance light could have traveled to reach us since the birth of the universe. Light moves fast, 299,792 kilometers per second, but the universe is nearly 13.8 billion years old. That means, in theory, we should be able to see objects that are 13.8 billion light years away, right? Not quite. Due to the expansion of the universe, space itself has been stretching. So while light has been traveling for 13.8 billion years, the objects that emitted that light are now much farther away, roughly 46.5 billion light years. This forms our particle horizon, the limit of our visible universe. Astrophysicist Edward R. Harrison, in his book Cosmology, The Science of the Universe, put it best. The particle horizon is our cosmic limit, the portion of the universe causally connected to us. Everything beyond this horizon, it exists, we're almost certain, but its light hasn't had time to reach us yet. The particle horizon tells us about the past, what regions of space have influenced us since the Big Bang. It's a hard stop, no light, no observation. Now, imagine the event horizon, a boundary in time, not space. This is not to be confused with a black hole's event horizon. In cosmology, the event horizon defines the farthest distance from which light emitted now can ever reach us in the future. Due to the universe's accelerating expansion, some galaxies are moving away from us faster than light, not because they're speeding through space, but because space itself is expanding. Current estimates place this cosmological event horizon at around 16 to 18 billion light years. Any light emitted today from objects beyond this boundary will never reach us, not in a trillion years, not ever. So if the particle horizon defines our past visibility, the event horizon defines our future invisibility. It's the ultimate farewell. Even if we sent a spaceship traveling at near light speed, it could never reach galaxies beyond this limit. NASA's IPAC and Explaining Science both confirm that this horizon exists due to dark energy, the mysterious force accelerating the universe's expansion. Just imagine, every second, more galaxies are slipping past this boundary, like ships sailing beyond the curvature of the Earth, never to be seen again. Next, we meet the Hubble sphere. This one's trickier. The Hubble sphere is the distance at which cosmic expansion causes galaxies to recede from us at the speed of light. Based on the current Hubble constant, approximately 67.4 kilometers per second per megaparsec, This boundary lies at about 14.4 billion light-years. Here's the kicker. Some galaxies are already beyond this sphere, and we can still see them. How? Because the light they emitted long ago, when they were within the Hubble sphere, is just now reaching us. Cosmologist Sean Carroll explains it this way. The Hubble sphere is not a true horizon. Galaxies can cross into and out of it. It's not a causal barrier. It's more like a dynamic threshold, shaped by the expansion rate of the universe. If dark energy continues to accelerate space, more galaxies will pass this line. And while we may still see their ancient light, we'll never observe their future. This links directly to cosmological redshift, the stretching of light waves as space expands. As galaxies recede faster, their light is redshifted more dramatically until it becomes undetectable. Each horizon defines a different cosmic limit. The particle horizon is our past light cone, what we can see. The event horizon is our future light cone, what we will never see. The Hubble sphere is a snapshot of how fast things are moving away due to expansion. These concepts might seem abstract, but they're baked into our technology. The James Webb Space Telescope peers deep into the past, up to galaxies just 300 million years after the Big Bang. But it can never see beyond the particle horizon. Similarly, when mapping future surveys like Euclid or SKA, astronomers have to account for redshift distortions, expansion limits, and horizon effects. Why does this matter to us? Because it reminds us of our place, not in a flat world, but in a vast, expanding, accelerating universe. We are bound, cosmically, by the laws of physics. Even with the fastest probes and most sensitive detectors, there will always be parts of the universe forever hidden from us. It's a humbling realization, and one that scientists like Carl Sagan, Stephen Hawking, and Brian Greene often reflected on. Sagan once said, "We are like butterflies who flutter for a day and think it is forever." And yet, within our observable slice, we have discovered so much: galaxies, dark matter, gravitational waves, and maybe even hints of other universes. Understanding these cosmic horizons is not about giving up. It's about embracing the mystery. The more we know about our limits, the more we appreciate what lies within them. As we peer deeper into space, we are also peering further back in time. But no matter how powerful our instruments become, there will always be a horizon, a limit to what we can know. And beyond it, only questions, waiting for the next generation to ask. In 1965, two radio astronomers made a discovery that would echo across the cosmos. A faint hiss, a signal from the depths of time, turned out to be the oldest light in the universe. This was the cosmic microwave background, or CMB. This chapter unpacks that ancient afterglow, what it reveals about the origin and nature of our universe, and how it became the single most powerful piece of evidence for the Big Bang theory. In Holmdel, New Jersey, researchers Arno Penzias and Robert Wilson were calibrating a large horn antenna for satellite communication when they stumbled upon something unusual, a persistent background noise. They tried everything to eliminate the interference, even cleaning pigeon droppings from the dish. But the signal remained. That signal turned out to be the cosmic microwave background, radiation left over from the Big Bang itself. Across town, physicist Robert Dickey at Princeton had theorized such a signal should exist. When the teams connected, history was made. Penzias and Wilson received the 1978 Nobel Prize in Physics for their accidental but groundbreaking detection. The CMB is a faint glow of microwave radiation that fills the entire sky. It's uniform in every direction but exhibits tiny fluctuations in temperature, just 1 part in 100,000. It originated roughly 380,000 years after the Big Bang, a moment called recombination, when the universe had cooled enough for protons and electrons to form neutral hydrogen. Before this time, photons couldn't travel freely. They were constantly scattered by free electrons. But at recombination, space became transparent. and light could finally move through it. That light is the cosmic microwave background. Today, it's stretched into the microwave part of the spectrum due to cosmic expansion, with a temperature of about 2.725 Kelvin. The CMB is, as P.J.E. Peebles, another Nobel laureate in cosmology, described, the Rosetta Stone of cosmology. It provides a snapshot of the universe in its infancy. Though nearly uniform, the CMB has slight variations, anisotropies, measured by satellites like COBE, 1989, WMAP, 2001, and Planck, 2009. These fluctuations represent tiny density differences in the early universe. Where the CMB was slightly warmer, matter was slightly denser, and gravity began to clump it. Over billions of years, these clumps evolved into galaxies, clusters, and superclusters. The Planck satellite provided the most detailed map of the CMB ever, revealing precise data about the age of the universe, approximately 13.8 billion years. The composition, approximately 5% normal matter, approximately 27% dark matter, approximately 68% dark energy. The shape. The universe is flat to within 0.4%. These measurements are so accurate they've become the standard model of cosmology, known as lambda cold dark matter. Beyond temperature, the CMB also carries polarization patterns. These are subtle signatures of the way photons scattered during recombination. Scientists classify these into E modes and B modes. E modes confirm the density fluctuations and align with inflation predictions. B modes could provide evidence for primordial gravitational waves, ripples in space-time caused by inflation. In 2014, the BICEP-2 experiment claimed to detect B modes. The excitement was palpable. But later analysis revealed much of the signal came from galactic dust. The hunt for primordial B modes continues. Still, these efforts demonstrate how the CMB offers a unique window into physics at energy scales far beyond any Earth-based collider. One of the strongest pieces of evidence for cosmic inflation, the rapid expansion of space fractions of a second after the Big Bang, comes from the CMB. Inflation theory, proposed by Alan Guth in 1981, predicted the near uniformity of the CMB with tiny, quantum-driven variations. And that's precisely what we observe. The flatness, horizon, and monopole problems of the original Big Bang theory are elegantly solved by inflation. And the scale-invariant spectrum of fluctuations in the CMB, a signature of quantum fields stretched by inflation. As Guth remarked, the universe is the ultimate free lunch. The seeds of all structure, galaxies, planets, life, were sown in the quantum noise of the inflating universe. Extracting the CMB isn't easy. Our own Milky Way emits radio, infrared, and microwave signals that interfere. To get a clean signal, scientists must subtract this foreground noise. The Planck team developed sophisticated algorithms to separate CMB from galactic emissions, revealing a pristine map of the early universe. This effort requires collaboration between astrophysicists, computer scientists, and statisticians. It also shows how modern cosmology is as much about data science as it is about telescopes. One emerging puzzle is the Hubble tension, a discrepancy in the universe's expansion rate. Measurements from the CMB, early universe, suggest a rate of about 67.4 kilometers per second per megaparsec, while local observations, like Cepheid variables and supernovae, indicate approximately 73 kilometers per second per megaparsec. Some scientists believe new physics may be required to explain the difference. Perhaps unknown particles, early dark energy, or modified gravity theories. The CMB, though ancient, is pushing the boundaries of modern physics. The CMB is more than a relic. It's a cosmic lighthouse, guiding our understanding of everything from the Big Bang to dark matter to the fate of the universe. It confirms our models, challenges our assumptions, and continues to raise new questions. As Stephen Hawking once said, We are just an advanced breed of monkeys on a minor planet of a very average star. But we can understand the universe. That makes us something very special. The CMB is proof of that understanding, a silent, ancient whisper that we've learned to hear. The universe has left behind a baby picture, etched into the fabric of space-time. It took 13.8 billion years for that light to reach us. And in its faint glow, we see everything, our beginnings, our structure, and our destiny. Between galaxies, clusters, and superclusters, there is nothing, or nearly so. Welcome to the cosmic voids, vast expanses of near emptiness that occupy most of the universe's volume. They are not simply gaps, they are a profound mystery. And in this chapter, we step into the silence of the cosmos. Cosmic voids are enormous, underdense regions of the universe, stretches of space containing far fewer galaxies than the cosmic average. While galaxies, gas, and dark matter clump into the cosmic web's filaments and nodes, voids fill the spaces in between. Typically, a void spans 30 to 300 million light-years across, though some supervoids exceed even that. The Bode's void, for instance, is roughly 330 million light-years wide, containing remarkably few galaxies for its size. When discovered in 1981 by astronomer Robert Kirshner and colleagues, it shook our understanding of the universe's large-scale structure. Void regions are not truly empty. They contain dark matter, intergalactic plasma, and sometimes even faint dwarf galaxies. But their average density can be less than 20% of the cosmic mean. Void detection emerged with deep sky surveys. The CFA Redshift survey in the 1980s was among the first to reveal large-scale structure, a filamentary web of galaxies surrounding vast empty spaces. Today, massive surveys like SDSS, Sloan Digital Sky Survey, and DES, Dark Energy Survey, map voids with increasing precision, helping us analyze void sizes and distributions, void shapes and alignments, gravitational lensing in void regions. Cosmologist Rien van de Weijgaert, a leader in void research, said, "Voids are nature's laboratories for the dark cosmos. They are clean testing grounds for studying dark energy, neutrino masses, and deviations from Einstein's gravity. Among the largest voids is the KBC void, named after Keenan, Barger, and Cowie. It stretches nearly 2 billion light-years across and is 20% less dense than average. Its discovery stirred debate, especially in relation to the Hubble tension. Some scientists hypothesize that being located inside a supervoid could make distant galaxies appear to recede more slowly, thus lowering the inferred Hubble constant from CMB data. Other supervoids include CMB cold spot, anomalously cold region in the cosmic microwave background, possibly linked to a massive void. Dipole repeller, a giant underdense region that may influence the Milky Way's motion. Though controversial, these giant voids force cosmologists to consider non-uniform models of cosmic expansion. In the early universe, quantum fluctuations seeded tiny over- and underdensities. As inflation stretched the universe, these became the blueprint for structure formation. Overdense regions grew into galaxies and clusters. Underdense regions were left behind. Dark energy further accelerated the evacuation of these regions, pulling matter away and deepening the voids. Simulations like Illustris and Millennium show how voids naturally emerge from gravitational evolution in expanding space. Voids respond differently to gravity compared to dense regions. As such, they are ideal to test modified theories of gravity, FR gravity, chameleon fields, massive neutrino effects. Surprisingly, galaxies in voids still rotate and cluster, albeit more slowly. Their structure may hint at alternative gravity models or interactions between dark matter and dark energy. Upcoming missions like Euclid and LSST aim to map voids more precisely, especially through weak lensing and redshift space distortions. One speculative idea is that voids could serve as signatures of collisions with other universes. Physicist Anthony Aguirre and others have proposed that bubble universes in the inflationary multiverse might leave imprints on the CMB or local void structure. The CMB cold spot, for example, has been proposed as a potential evidence of such a collision. Though no conclusive evidence exists, the idea that voids are scars from a deeper cosmological reality remains enticing. Void regions are often seen as existential symbols of emptiness, of the limits of knowledge, of cosmic humility. Carl Sagan reflected, "The universe is not required to be in perfect harmony with human ambition." And yet even in these near-empty stretches, science finds richness. In structure, in motion, in quantum memory. Cosmic voids are not failures of creation. They are part of the grand design, windows into gravity, dark energy, and perhaps realities beyond our own. In their silence, they speak volumes. Every story has an end. But what about the cosmos? Could the universe, in all its vastness, eventually run out of time? In this chapter, we explore the scientific scenarios that predict how the universe might meet its end, and the profound forces that will drive that fate. The most widely accepted scenario is known as heat death, also referred to as the Big Freeze. As the universe continues to expand, galaxies drift farther apart. Stars exhaust their nuclear fuel and die. Over trillions of years, white dwarfs cool, neutron stars fade, and black holes dominate. In this scenario, entropy, disorder, reaches its maximum. Thermodynamics teaches us that energy disperses over time. With no new stars forming and all usable energy expended, the universe becomes a dark, cold, and lifeless void. This process may take 10 to the 100th years, when even black holes evaporate. As cosmologist Katie Mack writes in The End of Everything, the universe doesn't go out with a bang, it ends with a whisper of radiation. In this dramatic endgame, the mysterious force of dark energy doesn't just accelerate the universe's expansion, it eventually tears it apart. This scenario depends on a hypothetical form of dark energy known as phantom energy, with an equation of state less than -1. If true, the acceleration becomes so intense that galaxies are pulled apart, solar systems unravel, atoms themselves are torn. The timeline? Potentially 22 billion years from now. Theorist Robert Caldwell coined the term Big Rip in 2003, outlining how even space-time itself would be shredded. According to many grand unified theories, guts, protons, the building blocks of atoms, may eventually decay into lighter particles. Though unproven, many models predict a half-life of approximately 10 to the 34th years. If protons decay, all matter disintegrates into radiation. Even the most stable structures, white dwarfs and neutron stars, fade away. Physicist Frank Wilczek, a Nobel laureate, remarks, "If proton decay is real, it's the slowest process we might ever observe, but also the most profound." In 1974, Stephen Hawking proposed that black holes aren't truly eternal. Through Hawking radiation, they slowly emit particles, losing mass over time. Small black holes evaporate quickly, Massive ones take 10 to the 64 to 10 to the 100 years. In the end, the universe contains only low-energy photons, electrons, and neutrinos. Information paradoxes remain unresolved. As Hawking famously said, black holes are not as black as they are painted. They are not eternal. The complete evaporation of black holes signals the ultimate fade-out. Some theories defy the idea of a final end. Loop quantum cosmology suggests that the universe may undergo a big bounce, collapsing and rebounding in cycles. Others, like the multiverse theory, propose that our universe is just one of countless others. As one dies, others are born. In The Elegant Universe, physicist Brian Greene writes, "The end of our universe may be just the start of another." Meanwhile, Roger Penrose's conformal cyclic cosmology posits an infinite succession of aeons, each a new universe born from the remains of the last. Though these scenarios span unimaginable timescales, contemplating the universe's end reminds us of our place in the cosmic story. As Carl Sagan said, "We are a way for the universe to know itself." Our species may be fleeting, but our questions, curiosity, and pursuit of knowledge resonate across epochs. The universe's ending isn't just a scientific forecast, it's a philosophical reflection. From slow dissipation to sudden destruction, the cosmos may conclude in silence or violence, but in asking how it ends, we understand more about how it began. And in that quest, our small voices echo in eternity. We often ask, how did it all begin? But what if the universe never truly had a beginning? What if time itself is an illusion? In this chapter, we journey beyond the classical Big Bang to explore quantum cosmology, where the rules of the very small reshape our understanding of the very large. According to the standard Big Bang model, the universe originated from an infinitely dense point known as a singularity. But singularities are places where classical physics breaks down, Einstein's equations of general relativity stop working, and quantum effects dominate. This is where quantum cosmology begins. The need to unify general relativity with quantum mechanics has led to radical new ideas about the universe's birth. In the 1980s, physicist Stephen Hawking and James Hartley introduced the no-boundary proposal. They suggested that the universe has no initial boundary in time. Instead of a singularity, time behaves like a spatial dimension near the beginning, smoothing out the origin. Hawking explained, "The boundary condition of the universe is that it has no boundary. This idea removes the need for a start in the classical sense. The universe just is." Another promising theory comes from loop quantum gravity, LQG, developed by physicist Abhay Ashtekar and colleagues. It proposes that space-time is made of discrete quantum loops. When applied to cosmology, LQG replaces the Big Bang with a big bounce. Instead of an origin point, a previous universe collapsed and rebounded into ours. This cyclic model suggests no singularity, a pre-existing contracting universe. Quantum gravity effects dominate early universe physics. Ashtekar states, "The quantum bounce offers a new paradigm. The universe didn't begin with a bang, but with a rebound." String theory, which unifies gravity with quantum mechanics, introduces the idea of extra dimensions and multiple universes. Physicist Brian Greene in The Elegant Universe explores how our universe may be one of countless others, floating in a grand cosmic multiverse. String theory supports brane cosmology, where universes are three-dimensional surfaces, branes, floating in higher dimensional space. Eternal inflation, where inflation never stops, spawning infinite bubble universes. These ideas suggest the Big Bang may just be a local event in a much larger reality. A provocative theory by physicist Lee Smolin proposes that black holes might create new universes. Called cosmological natural selection, the idea is each black hole forms a new universe with slightly different physics. Universes that produce more black holes are more fit. This concept ties the end of stars to the beginning of new cosmoses, forming a kind of cosmic evolutionary tree. In quantum mechanics, vacuum fluctuations allow particles to briefly appear and disappear. Some physicists believe the universe could have emerged from a quantum fluctuation of the vacuum. Physicist Edward Tryon famously quipped, "The universe is simply one of those things that happens from time to time." Another model, called quantum tunneling from nothing, proposes that the universe tunneled into existence spontaneously, a quantum event requiring no cause. These models challenge our deepest intuitions about time, causality, and existence. If time began with the universe, what does "before" mean? As physicist Sean Carroll notes, the universe doesn't need a cause any more than a circle needs a beginning. Quantum cosmology opens doors to understanding the very nature of reality, but it remains speculative. Much depends on future discoveries in quantum gravity and cosmological observations. Perhaps the universe had no true beginning. Perhaps it has cycled endlessly or emerged from a deeper quantum sea. Whatever the truth, our quest to understand it leads us into the heart of mystery, where physics meets philosophy. Since the dawn of time, we've looked to the skies and asked, why are we here? What lies beyond? And how does it all work? In this final chapter, we celebrate the tireless journey of discovery that defines humanity's quest to understand the universe. Long before telescopes, ancient civilizations tracked the stars. From the Babylonians charting Venus to the Maya calculating solar eclipses, our fascination with the cosmos is timeless. The invention of the telescope by Galileo Galilei in 1609 launched a scientific revolution. With it, we discovered moons around Jupiter, sunspots, and the phases of Venus, evidence that Earth wasn't the center of everything. Galileo wrote, "All truths are easy to understand once they are discovered. The point is to discover them." His defiance of dogma planted the seeds of modern science. Today, humanity wields a powerful arsenal of tools. Hubble Space Telescope revealed galaxies billions of light years away. Planck satellite measured the CMB with stunning precision. LIGO and Virgo detected gravitational waves from colliding black holes. James Webb Space Telescope, JWST, peering into the earliest galaxies. Each breakthrough extends our cosmic reach. Projects like Euclid and the upcoming CMBS-4 experiment aim to decipher dark energy and the universe's expansion rate. As astrophysicist Wendy Friedman says, precision cosmology is not just about measuring numbers, it's about testing our deepest assumptions. CERN's Large Hadron Collider LHC smashes particles to glimpse conditions just after the Big Bang. Discoveries like the Higgs boson help explain why particles have mass. Meanwhile, neutrino observatories, like IceCube in Antarctica, detect elusive particles from deep space, offering clues about supernovae and black holes. Fabiola Giannotti, Director General of CERN, notes, "Particle physics and cosmology are two sides of the same coin. One probes the smallest scales, the other the largest." Modern astronomy generates petabytes of data. To manage it, scientists use machine learning to detect patterns, classify galaxies, and simulate cosmic evolution. Public platforms like Zooniverse empower citizens to assist in real research, from spotting exoplanets to identifying gravitational lenses. This democratization of science enhances discovery and connects people to the cosmos. As astronomer Chris Lintott puts it, "The universe is too vast for any one of us to comprehend, but together we can reveal its secrets." Science doesn't just change what we know, it transforms how we think. Contemplating the universe forces us to confront questions of existence, meaning, and time. Are we alone? Is reality deterministic? What is consciousness in a quantum world? Physicist Sabine Hossenfelder remarks, "Science can describe the universe, but only we can decide what that means for us. The human journey in cosmology is as emotional and philosophical as it is empirical. What lies ahead? Some key missions and ideas shaping the future. Square Kilometer Array, SKA, the largest radio telescope ever built. LISA, a space-based gravitational wave detector. Quantum gravity theories, searching for a unified framework. Time crystals and exotic matter, expanding our understanding of physics. Private spaceflight may also fuel scientific exploration, from moon bases to interstellar probes. As Elon Musk said, we need to be a multiplanetary species to ensure the survival of consciousness. Ultimately, humanity's quest to understand the universe is a mirror reflecting our deepest nature. We are explorers, storytellers, thinkers. From ancient sky gazers to quantum physicists, the impulse to know binds generations. Carl Sagan said, "Somewhere, something incredible is waiting to be known." That pursuit, endless, imperfect, profound, is what makes us human. From the first stargazers to the scientists mapping galaxies, we are part of a great cosmic narrative. As we close this journey, remember, the universe isn't done revealing its secrets, and we are not done asking. If you found meaning, wonder, or awe in this series, subscribe, share, and stay curious, because the journey never ends.